section 9.1, we're going to take a look at determining probabilities. As with every 0.1 section, right, 6.1, 7.1, now 9.1, we're going to have a lot of vocab stuff. So that's where we're going to get started with some terms. So our first term is the word experiment. Not necessarily scientific, but this is an activity whose results can be observed and recorded. Okay, anything that can have the results observed and recorded is considered an experiment for what we're working with. Mostly we're going to be working with mathematical experiments, obviously. An outcome is each possible result of an experiment. So sometimes that is a result of the experiment, like if the experiment is shooting a basket, the result is either you make it or you miss it. Sometimes you're looking at things with results that are, let me pause this. Okay, we'll try again. So an outcome is simply the possible results of an experiment. The experiment sometimes just has two results. That's a possibility, right? You win or you lose. You make it or you miss it, those kinds of things. But if you think about some other kinds of experiments, maybe you're playing a game where you're drawing a card from a deck of cards. Well, every single card would be an outcome, right? Because there's 52 different cards on a standard deck. Maybe you're tossing a die. Well, a standard die has 6 different sides, so there's 6 possible outcomes if you're looking at that scenario. So it just depends on the experiment you're working with. The sample space is just a set of all possible outcomes. So if you were looking at your deck of cards, it'd be the list of the 52 cards, right, the different cards. If you're looking at the die, you'd be looking at a list of the 6 different outcomes on the die, those sorts of things. And it's just a sample space is a set. Sets are written in braces like this. That was a terrible brace, but you have the right idea, I hope. And you list all the outcomes in between. And then an event is a subset of the sample space. So an event, if I'm doing a deck of cards, might be that I drew a red card. An event might be that I drew a 7. An event might be that I drew a face card. Okay, so it's a collection, sub-collection of things that are usually multiple options. If I were rolling the dice, the event that might be that I rolled a prime number, or an even number, or an odd number, or a number 6 or a 5 or 6, right? A sub-collection of different events. So theorem 9.1 talks about the law of large numbers. This is Bernoulli's theorem, called the law of large numbers. And it says if an experiment is repeated a large number of times, the probability approaches a fixed number. So a really good example of this would be flipping a coin. So a coin has a 50-50 shot of landing on heads or tails, right? And you would assume that if you flipped the coin enough times, you'd have about a number equal of heads that you flipped up as you did tails. Okay, and lots, like big numbers, like 500 times, 1,000 times, you'd have it split about even. Right? So it only works for large numbers. The way we calculate probability when we're looking at these fixed numbers is this is the probability of this would be an event A. Okay? So the probability of event A happening or outcome A happening, whatever A is representing, is the number of ways that event or that outcome can happen, divided then by the number of items in the sample space. So let's talk about the dice because it's small numbers. If I was looking at the number of ways that I can roll an even, and I'm looking at dice, well, there's 6 different numbers on the dice, on the die. How many of them are even? Y'all have rolled die before. Come on. 3 of them are even, right? A 2, a 4, and a 6. So there's a 3 out of 6, and of course we would reduce just like we did back in chapter 6 when we were looking at fractions. We'll reduce the probability down to its simplest form, which would be 1 out of 2. So you would have a 1/2 probability of rolling an even number on any given roll. Mutually exclusive events are events where they don't have anything in common. So if we looked at our dice, we could talk about mutually exclusive events of rolling an even and rolling an odd. Now that's all the possibilities. Those are mutually exclusive and they cover everything. If I were looking at my deck of cards, I could do drawing a red or drawing a black, but I could also talk about, drawing a 7 or drawing an ace. I don't have any cards that are both 7s and aces, but it doesn't include every possibility in that scenario. Okay, Okay, so mutually exclusive doesn't mean it includes all the possibilities and they're just separated. It just means they're separated. No overlaps. The notation, and this is maybe familiar notation. It depends on if you've had number theory or a set theory type class. This notation right here is notation that we see in that. So these are two different events for what we're talking about, event A and event B. And then this symbol right here is the intersection symbol. So intersection very much means like the intersection of the streets. It's the overlap. So what they have in common. Or you can think of it as the overlap. And what this is saying is that it doesn't exist. There is no intersection. There is no overlap. That's what that symbol over there means. There isn't anything in it. Okay, that symbol truly means empty set, for those of you who've had number theory. But it simply means there's nothing in it. There's nothing in the intersection. Now, with any probability for an event, any event, the probability has to be between 0 and 1. So 0 means it can never happen. 1 means it always happens. So you can think of the 0 and the 1 very much like a percentage, 0%, 100%. Right? Something happens between 0% and 100% of the time. Like there's not a 110% chance it's going to rain tomorrow. Right? That doesn't make sense. The percentage is somewhere between 0 and 100%, or the probability between 0 and 1. The next one talks about what happens when things are disjoint. So if you have disjoint events, right, events that don't have any overlap, like we talked about before, then the probability that the event of either one happening is simply the addition of each of the individual events. Right, so if you wanted to know, for example, we're rolling a 6-sided die. If you wanted to know the probability of rolling a 1 or a 2, you can't do both at the same time if you're just rolling one dice, right? Those are disjoint events. I roll a 1, or I roll a 2, or I don't roll either of them. I mean, there's no in between. I can't overlap those categories. So when that happens, this is the same as the probability of rolling a 1 plus the probability of rolling a 2. Those are actually the same probabilities. So when I'm looking at that, the probability of rolling a 1 on a 6-sided die is 1/6. The probability of rolling a 2 on a 6-sided die is another 1/6. And that should make sense that rolling a 1 or a 2 means I have 2 possible outcomes over the 6 total. So that's the relationship that it's talking about happening on theorem 9. What are we on? 9.3. Okay, a couple more theorems, and then we're going to put them all into sort of a nice organized chart. Theorem 9.4 is the mutually exclusive one we just talked about. If they are mutually exclusive, the probability of the union plus the probability of the union of A and B, which means doing either of them happening at the same time, is the probability of event A and the probability of event B. So that's a continuation of theorem 9.3. Theorem 9.5 talks about complements. And again, your familiarity with complements probably hinges on whether or not you've had a set theory class or number theory specifically here. So this is an event happening. So this is event A. And this is the event of its complement, which means it's not A happening. Right? So if event A is you roll a 1, then event A complement is you don't roll a 1. You roll anything else. If event A is that you roll an even, then the complement would be that you roll an odd, because that's everything that are not evens. If you're drawing cards from a deck, if it's the event that you draw a 7, the complement is the event that you don't draw a 7. Everything but a 7 is what's included. Okay, so it's not the event happening. And what this is saying is that if you add the probability of the event and the probability of the event not happening, that's 100%. It's everything. Which should make sense, right? Probability of 1, the probability of not a 1, that's include all the possibilities. It's 100%, one or the other, right? So we get that probability equaling 1. And the other two are just adjustments to this formula. So if you take this formula, probability of event A plus the probability of the complement, n equals 1, and you subtract probability of A complement to the other side, you have the second equation. Or if you subtract the probability of A to the other side, you have the third equation. So they're just adjustments of the same formula. So these are all these theorems, and what we're going to actually do next is we're just going to put them all in a contained space, like all together. So these are a summary of our probability properties from those theorems. All the things that we just discussed put together in one sort of chart. So the first one is the probability of something that doesn't exist happening. Right? So what's the probability that's going to snow tomorrow? 0. It's not cold enough tomorrow to snow here, right? That is an impossible event for tomorrow, given that we know what the weather's doing today and what the predictions are. It's impossible. So that's 0. The probability of that is 0. The probability of a certain event, it's definitely going to happen. That's equal to 1. Right? So you've probably heard this before, but if not, it's always fun to listen to. It says, you worry about a whole lot of things that never happen. It's not true for your final. It's going to happen. There's going to be a final unless Jesus comes back first. We're having one. It's a certain event, 100% guaranteed event. Everything else has to lie then between the 0 and the 1. Between a never going to happen event and an always going to happen event. Somewhere in between are all of the other probabilities. Probability it's going to rain tomorrow. My phone told me this morning it's 40% chance. That's 0.4. Okay? Probability it's not going to rain would then be 0.6. Right here, this one tells you that if you have a disjoint set, right, if A and B have nothing in common, then the probability of A or B happening, that union means or, excuse me. So this right here, whoops, that showed up, okay, is the word or. The probability of event A or event B happening is simply the addition of their individual probabilities, probability of event A plus probability of event B. Now the next one we actually haven't talked about. It talks about what happens if the events do overlap. So this is a more generalized statement about what happens when the or is going to happen. This one says that I have the probability of event A happening plus the probability of event B happening, which is exactly what the previous line said. But then I have at the end the subtraction of their intersection. So why does that happen? Well, when I count the ways that A can happen and I count the ways that B can happen, if there's any overlap, I've counted some things twice. And a really good example of that would actually be cards. I don't know how familiar you are with cards. We'll talk more about cards at the end of the class. But if you wanted the probability that you drew a red and the probability that you drew a diamond, those overlap because diamonds are red, right? Which means if I counted up the number of red cards and I counted up the number of diamond cards and I added them together, I've counted some of the cards twice, right? So that's why you see this being removed here at the end, is I'm removing double counts. I'm removing the things that I counted twice. And if there are no things counted twice, then this would just be 0. It would collapse and it would become the previous line's equation. Probability of event A plus probability of event B. And the last one talks about that complement we talked about. So the probability it's not going to rain tomorrow is 1 minus the probability that it is going to rain tomorrow. Right? It's one or the other. Okay, so they have to add up to 1, and this is one of those 3 equations. So we're going to do an example with cards to show some of these things working out. So I'd like to run through some details about cards in case you're not very familiar with a standard deck of cards. I have a 7-year-old, and my 7-year-old is convinced that they're called garbage cards. So I don't know if you know what the game Garbage is, but it's about all that she can handle with a deck of cards right now at 7 years old. She knows how to play Garbage. So now you're going to all go Google it because it's a very simple game for young children, and I know most of you want to work with young children. And you can do it with a plain deck of cards. She's convinced that the decks of cards are called garbage cards. They're not. There's 52 cards in a deck, okay? Half of them are black and half of them are white. So what's half of 52? 26. So we have 26 red, 26 black. We have 4 suits of cards. I mentioned diamonds before. Diamonds, which are red. Hearts are also red. So there's 13 of each of those decks, or of those suits. 13 hearts, 13 diamonds. We have 2 suits that are black. We have clubs and we have spades. So there's 13 clubs and there's 13 spades. Okay, so that's kind of the color arrangement of the cards. You also have numerical arrangements of the cards. So in a deck of cards, you don't have the number 1. The numbered cards go from 2 to 10. So there's 9 number cards in each suit. So there's 9 number cards that are hearts, 9 that are diamonds, 9 that are spades, and 9 that are clubs. Okay? So 9 times 4 would be 36. So there's 36 number cards. You have your face cards. Your face cards are jacks, queens, and kings. All right? And there's 3 in every suit. So there's a jack of hearts, a jack of diamonds, a jack of clubs, and a jack of spades. I think that's what I left out. So there's 3 of each suit. There's 4 suits. There's 12 face cards. And then we have aces. And aces do not count as face cards, and they do not count as number cards, either one. All right? So they're their own category. And there's 4 aces, 1 in each category. Of course, we have evens and odds. We'll get to that at the very end of this question. We just count the number of the numbers between 2 and 10 that are even and 2 and 10 that are odd. Okay, so this question is actually asking us to compare things that are likely or not likely, equally likely or not equally likely. So I mentioned face cards a moment ago. There's 3 face cards in each suit, and there's 4 suits. So how many face cards were there? There are 12. So there are 12 face cards. I'll write mine underneath, although you can write yours out to the side if you want to do it there instead. I think I'll change colors just to try to distinguish it a little bit better. 12 face cards. How many cards were there total in my deck? 52. So there's 12 out of 52 that are face cards. Not a face card. Okay, so I have 52 cards. 12 of them are face cards. How many of them are not face cards? 40. How'd you get 40, Casey? Which is what I think Hannah was trying to tell me. You can subtract them. Yeah, so there's 40 cards. It would be the number of cards in the aces. That would be not face cards. So there's 40 out of 52 that are not a face cards. So is it equally likely that you will draw a face card and not a face card? Are those equally likely events? No, because the probabilities aren't equal. 12 out of 52 is not the same as 40 out of 52. So these are not equal. How about clubs? How many clubs did we say there were? 13. Out of how many cards? 52. How many diamonds? 13 out of 52. Hearts? 13 out of my 52. And my spades are also 13 out of 52. So there are 4 different events here, drawing each one of those different suits. Are those events equally likely? Yes, they're all equal probabilities, so these are equally likely. So I'll just write equal here. Black and red. How many black cards were there? 26 out of the 52. How many red cards? 26 out of the 52. Are these events equally likely? Yes, these are equal. All right, I have the last one. It has lots of pieces, so we'll do them each individually. How many kings? 4 out of 52. Queens? 4 out of 52. Jacks? 4 over 52. Aces? 4 over 52. And if I stopped right there, the events would be equally likely, right? Because those were all 4 out of 52s. How about even cards? All right, so we have 2, 4, 6, 8, and 10. There's 5 even cards of each suit, and there are 4 suits. So how many even cards are there? 20 out of 52. How about odd? Do not assume that even and odd match, because that doesn't always work and everything. So I have 3, 5, 7, and 9. That's all the odd cards I have. There's 4 in each suit, and there's 4 suits. So how many odd cards? 16. So these are the, what do I have? 6 different probabilities that I'm considering. Are they all equally likely? No. So these are not equally likely. Okay, any questions on that? Okay, so card games, dice games, coin flipping, roulette, lotteries. We're going to see a lot of these things happening in Chapter 9, but we're also going to see problems where we are looking at probabilities within different experiments that are just scenario-based, like this one. A Civ class is composed of 21 men and 34 women. That sounds about right, doesn't it? That over you? There are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, and 3 math majors. Now, in order for what I'm about to say to work, the next statement has to be written in, and we have to know it. And it says that there are no double majors. Okay, so I get that sometimes there are double majors, but in our scenario, the way it's set up, there aren't. It says if a single student is chosen at random, what is the probability that says student is? And it gives us some language, right? Some scenarios to follow. So the first thing is that it's female. The student is female. So how many females were there? 34. How many people were there total? 55. We didn't add them up, but you guys added them up very quickly. We had, whoops, that's not what I wanted. 34 and 21. So there are 55 total people in this class. So 34 out of 55. Okay? If we have the ability to reduce it, we will. This one doesn't, because 55 is only divisible by 5 and 11, and 34 is not. So we're done with it at this point. How about a science major? 12 out of 55. Can I reduce that? No. How about English or religion? So we don't have any double majors. So these are independent, right? They're disjoint from one another. They are not considered possible to be at the same time. So I need to know how many English majors I have, which is 13. So that's 13 out of 55. And how many religion majors?
There's 13 religion, 5 English.
Oh, did I write them backwards? Thank you. So 5 English, 13 religion? Is that right? Okay. So 5 English, 13 religion, just so that I got them in order of the way that the language is structured. And then 5 55ths plus 13 55ths would be 18 55ths. Okay? And again, it doesn't reduce. Now the last one says neither a math major nor a science major. And I put this one in here because I want to show you that there's 2 different ways to work this problem. All right? So one way to work the problem is to figure out how many math and science majors there are. So how many math majors are there? 3. And how many science? 12. So that means there's a total of 3 plus 12, which would be 15. So 15 are math and science. How many aren't? 40, because there was 55. So the answer would be 40 over 55. And we're doing that from the perspective of saying that I have, actually, let me rewrite it here. 3 plus my 12 over my 55, which gave me 15 out of 55. And then what I'm really doing is I'm taking 1 minus 15 over 55, or 55 minus 15. Can you think of another way to do this problem? Yeah. Because we know all of the other majors and how many there are, we could add them up directly. So we could add up the religion, the education, and the English. Were those my other 3? We could add up those individual pieces. Just visually, do those add up to 40? I hope so. Does it work? Yes. Reagan says yes. Fabulous. So we can add them up. Now you'll notice that these questions did not say anything like a female religion major, right, or a female education major, because I don't have any information that allows me to differentiate between those as it's given, right? Those categories could, in fact, would overlap in most cases, and I don't know how they overlap, so the questions don't actually hinder toward, or lean toward that. 40 out of 55 actually does reduce, so we probably should do that too. What do they both divide by? 5. So if I divide them both by 5, I'll get 8 out of 11. So when they do simplify or reduce, we will do that. That was the only one it did. Any questions on that? Okay, what we're going to look at next is the next page is 3 different kind of type C kind of questions, right, from your book, those collaboration or communication or whatever they're calling them at this point now in your book. So you can kind of see what kind of things show up in that section. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What do you say? So anytime you're trying to reply to somebody, you need to think about, do you agree or do you disagree? And then you need to think about justifying why you believe what you believe about it. Okay, so the first question is the student correct or is he incorrect, in your opinion? Is the probability of tossing tails on the next toss greater than the probability of tossing heads? No, it is not. So this is incorrect. Okay, so this is the premise that we're working under. Now we have to justify why we believe it is an incorrect assertion. So why is the student incorrect?
No matter how many times you flip the coin, heads or tails doesn't change it being option.
Okay, so you're exactly right. Sorry, I keep forgetting I'm locked in. Can't keep moving. So you're exactly right, Mel, and I'm going to say it in a little bit different way. So the individual flips of the coins have nothing to do with what happened previously, right? Every single time I flip my coin, I start over with a 50-50 shot. We'll encounter another scenario like this next time when we look in section 9.2. The same thing happens when you have babies being born. Okay, if you've had 5 girls, try number 6 is not going to be any less equally likely to produce another girl, right? I have a family I know, they have 6 daughters. I think they were trying for a son. It's a lot of daughters. But they're no more likely on event or try number 6 at getting a boy than they were on events 1 through 5, right? It's the same thing every single time. So each coin flip is independent of previous flips. Each, whoops, I'm running out of space there. Each flip has a 1/2 probability of heads or tails. That's the reality. And that's actually enough to make his assertion false. But he says something else that's a little bit weird too. Did you catch it? What else in his statement is a little awkward or odd? It's not that it's a fair coin. Good try. Why is the law of large numbers odd? Yeah, 5 is not a large number, right? It doesn't apply to this, like you were saying, because 5 is not a large number. So if he made the same argument and he was talking about having flipped it 500 times, it would no more be true because we've already stated that each flip is individual. Although we might wonder at that point if we've actually got a fair coin, right? I mean, that would be a legit question at that point. But Bernoulli's law of large numbers doesn't apply here anyway because there's not a large number of things happening. It's a small number. So we could also say, oops. Also 5 is not a large number. So Bernoulli's, get a spelling for that. Bernoulli's law, or the law of large numbers, does not apply. So it's a good idea when you address a student's statements that you make sure to cover all the pieces of the things that they say. So if there's something to be said about more than one piece, we want to make sure we address all the different pieces. Because what we don't want is we don't want to say, for instance, only address the Bernoulli's law of large numbers, and then now he comes and he says, well, what if I did it 500 times? Like, okay, well, now you got a large number, but we've got other issues now, and there's still another issue at play here. We want to address all the issues that are at play. All right, let's do an example number 4. The following spinner is spun 100 times. Joe claims that the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture? And what is the probability that 4 will occur on any spin? There's 2 questions. We'll start with what would you tell Joe about his conjecture? Is he right or is he wrong? He is wrong. So why is he wrong? Go for it, Emily.
The spinner itself is still in the center of all the numbers, so they're still equally portioned for each number.
Okay, cool. Yeah, so the spinner spins through 1 through 4. I'm going to say through equal angles. Right, the angle measure that it spins through for this angle that's kind of marked as 1 is the same as the angle at 2, the angle at 4, and the angle at 3. They're all equal angles that it's spinning through. The reality is that the area of the regions is irrelevant. Because the spinner is, we'll say, is passing through angles instead of area. Or through angle measures. I'll just say through angles, it's shorter. We'll go with that. The other question then it says is, what is the probability that 4 will occur? How likely is it that we're going to spin and we're going to get a 4? Somebody say it loud.
1/4.
1/4, thank you. Probability is 1/4. Each of those angles is equal. They're all 90-degree angles. There's 4 angles there, so it is a 1/4 probability. Now we're going to take example 4, that is the spinner, this picture, and we're going to change it slightly. And instead, on example 5, we're going to consider the same image, but now it's a dartboard. Okay, the experiment changed. The image didn't, but the experiment changed. So if we have a dartboard, will that change our reply to Joe? Yes, it will. So is his conjecture, if it's a dartboard instead and we're throwing darts, is his conjecture going to be true in this scenario? Yeah. There's more space in the location of 4, right? The 4 corner or whatever, for the dart to hit than it is in the other 3 locations. So here, his conjecture is correct. Since region 4 has the most area, we are more likely to hit hit with the dart. We can't actually tell you exactly how probability works, though, for that, right? This image, because of the way it's divided up, does not lend itself for us to be able to say, hey, it's, like 50% of the chance that we're going to hit region 4, or 72%. We don't have the ability to know that with this image. So we can't actually calculate. So we not actually calculate the probability. We could, however, say that for sure the probability of hitting the 4 is greater than the probability of hitting the 3, or the probability of hitting a 4 is greater than 2 or 1, right? That's the best we can do as we're relating them. We might even be able to make some sort of a relationship that at least says that probability of event 1's the least, right? I don't even know that for sure we can really say that 2 and 3 are the same, although they visually seem like they probably are, right? Without knowing a bit more information, we can't really get to that point. But we could say something like that. All right, we're going to do one more example. We saw an example with some COVID data in section 7.4. And this is one more place where I was able to use some of that data to show you how you can think about data in the real world. So recall, we talked about this, on August 1st, 2020, the total number of positive COVID cases in the state of Oklahoma stood at 37,731. Population of July 1st, again, I wish they were the same date, but they're not, was 3,956,371. So on August 1st, what was the probability that if you interacted with someone, you were interacting with someone who at some point had tested positive for COVID? Okay, so we actually looked at this before, but we looked at it from a different point of view. Here we're looking at it from a probability point of view, right? So our comparison that we're making are the people who are positive compared to the total population, right? That's the comparison that we're making. So that's my 37,000 number. 37,731 was the positive caseload at that point. And my total number in Oklahoma at that point was 3,956,971. And if you grab your calculator to do that, we're just going to go with 4 decimals of accuracy is probably sufficient on most probabilities. Your book tends to do that on some of their problems for cards and things like that too. So we'll go with 4 decimals. What do you get for your 4 decimals if you do this division? It's got to be something between 0 and 1, right? Caleb, I see you putting yours in. What did you get?
0.0095.
Yes, that's what I have too, 0.0095. So what does that actually mean? Well, it might make sense a little bit better to us in terms of fractions. And we spend a whole section turning fractions into decimals and back and forth. What place value is the 5 in? The 10,000th place. So this means 95 out, or in 10,000, we'll say it that way. So if I had 10,000 people in a room, 95 of them in that room at that point would have had COVID at some point. If we had rounded to 3 decimal places, we would have gotten a little bit different number. The number actually would have rounded up to a 1 here, like that. Right? If we'd rounded it to 3 decimal places, it would actually have been 0, 1, 0 at the end. In other words, we would have really just had a 0, 1. So it was about 1 in 100. If we had rounded a little bit differently. So 95 in every 10,000 people, or 1 in 100 people. We'll do one more problem with some of this data from COVID. Also on August 1st, it had been reported that there had been 549 deaths with COVID, and 30,282 people had recovered from COVID. On August 1st, what is the probability of interacting with someone who is currently infected with COVID? Okay, so let's go back over here. It said that there were 37,731 people who tested positive. Over here, it tells us 549 died and 30,282 recovered. Okay, so they're not all positive at the same time, right? That's how these numbers are playing out. You've got a proportion of people who die, you've got a proportion of people who recover, and you have the total number of people who tested positive to begin with. So we have, our 37,731 who tested positive, the 549 that died with COVID, and then the 30,282 that recovered. Out of that same 3,956,971 number. This was all August 1st of a year ago data. So if we do all of our subtraction on top, what do you get?
6,900.
Yep, 6,900. Out of the 3 million, 3,956,971. Okay, so again, we'll use our 4 decimals of accuracy. Go ahead and take your calculator and divide it out. If you use 4 decimals of accuracy, what decimal will you get? Did you get it?
0.0017.
Okay, good. And again, that 7 is in the 10,000s place. So this means 17 in every 10,000 people. So if you went into a room of 10,000 people, 17 of them would actually have COVID at that given moment. Okay, that's what that means with those numbers playing out the way that they've written. If we had rounded to 3 decimal places, this would have been 002. So depending again on how we round, you could say that this is about 2 in 1,000. So in every 1,000 people, there's about 2. Sometimes smaller numbers make it a little bit more reasonable because I don't know about you, but I kind of don't think I interact with 10,000 people in a day. That's probably an unrealistic number, but if you do into hundreds or into thousands, we might think that's a little bit more realistic for our world. All right, so here's what we're going to do. We've finished 9.1, but we haven't done group work, okay? So this 9.1, we're going to table it for now, and we will do group work next class period, Friday, and the homework for 9.1 will be due on Monday, which means, I know you probably have other things in other classes, but it means for this class you don't have any homework to do between now and Friday, and I would strongly encourage you to do something with your redos between now and Friday since you do have that ability, all right?